All right, so in this video, I'm going to explain the idea of differentials. So we've just talked about linearization and linear approximation, and differentials are sort of a way to rephrase the idea of linear approximation and think about little changes in x and little changes in y. Okay, so let's say you've got a function y equals f of x. You pick a value, an x value c, and you perform a linearization. You calculate a linearization there. So there's our tangent line, y equals L of x. Okay, let's say you change x by a little bit. So from c, we're going to move along our x-axis by some amount to, let's say, over here. Let's have this be c plus some change in x. And the change in x is, of course, delta x. We've used that before, back when we were talking about derivatives. So that means this distance here, from here to here, that distance there is delta x. Okay. Now, let's extend that line out a little bit further here. Okay, that delta x goes from there to there, right, between those arrows. But if I just extend that line out a little bit, it gives me something to measure from. If I measure the actual change in the y coordinate, as x changes from c to c plus delta x, if I measure the change in y up to the function up here, that would be that distance right there. So that distance there, up to this point here, let's see, I want to graph that sort of like, I'll put it like this. That distance there that I have that sort of brace around, that distance there is delta y. All right, I'm being very careful about the way I draw this because I'm going to have to add some more things to this picture in a moment. But so far we have that. So delta y is the change in the function f of x occurring due to change in x, which is delta x. Okay, so remember y depends on x via this function, f of x, so a change in x causes this change in y, right? So now, differentials are basically the same idea of change in x and change in y, except instead of for the function f, it's for the linearization of that function L. So actually, let's go ahead and do this in red so that it kind of corresponds to a linearization. So the linearization, the x input doesn't change at all, right? Like we're not modifying anything about x. So so for x, the change in x is the same. Now for linearization, or sorry, for differentials, we're going to use, instead of delta, we're going to use the letter d. So instead of talking about delta x, we'll talk about dx. But delta x and dx are exactly the same, because whether you're talking about the function f or its linearization L, change in x is change in x, okay? They're the same thing. But when it comes to the change in height here, the linearization changes by a different amount. Right there. That is dy, okay? So what you want to think about is that dy is different from delta y. dy is more about the change in the linearization of that function for a corresponding change in x. Okay, so what we've got here is then, let me think about this for a second here. We can say that dy equals the change in L of x occurring due to change in x, which we're going to call dx this time. Okay, and then we could write dx equals delta x, and dy is going to be equal to, if I calculate the slope of this line, okay, slope of tangent line, remember that's y prime, which is dy over dx. Now, the notation dy over dx, normally we've been thinking of that as just, that's the derivative, But now we can think of dy and dx as like independent things, where dy is the vertical change in the slope of the linearization and dx is the horizontal change. This is literally just, rise over run. So what we can take out of this is that dy is going to be y prime times dx. So there we go. That's what I wanted to write over here. dy equals y prime times dx. Essentially, you can calculate the differential dy by taking the derivative of the function f and then multiplying that by dx. And then for any particular dx, you'd be able to multiply it by y prime if at c, like you'd evaluate the function at c, and then get the resulting change in the linearization. Okay, so there's some sort of formulas we're going to work with. And then now with this vocabulary we've established, the idea of linearization is basically that delta y, the actual change in the function value, is approximately equal to dy for dx values close to 0. So this is rephrasing that idea of linearization in terms of the differential. The delta y and the dy are going to be approximately the same as long as you take a dx that's small. And if you look at this picture, the change, like the change in f and the change in L are going to be, closer to each other if you look at, if you take a point which is closer to c. So like down here, say that's your, right there, that's your delta y. Then the corresponding change in L is going to be that right there. That's your dy. And they're pretty close to each other, right? They're pretty close in height, or like the length of those two little lines are pretty close. And it's only going to get more accurate as you get closer to C from either the left or the right. Okay. In the next video, we'll do an example with a specific function.